Crystal, you there?
I'm here.
All right. There you are. All right. So we are in our last week, and this will be the last time you hear me yap. Unless you want to do classes again next semester and just repeat the whole thing over again. Oh, how exciting, huh? But we are, so there's no test. There's no test for today's module. For the module we're doing today, it'll just all be in part of the final. And so we just go to the final on Thursday. It'll just be really easy, except for you, Crystal. It'll be hard for you. And then we will, I'll give you like 2 hours to do the final. You can do it like twice. It's a piece of cake. It is every question you've already answered. So not every question. There were 86 questions. I ditched 36 of them. So there's only 50 questions. So it's not too bad. So without further ado, let's get on. Is everybody comfortable with the class? Everything's good so far?
Yes.
All right.
Yep.
All right. Okay. Come on, baby. Load up. There we go. All right. So we've come full circle back around on these things here, back to the computer systems. So this module is on onboard diagnostics. And so what is OBD or onboard diagnostics? Well, today's engines are all computer controlled, whether they're gas, whether they're diesel, they're all computer controlled ad nauseum. Okay. They're run by what we call feedback systems. And I'm sure I'm going to be a little bit redundant on some of this stuff. You've probably heard it in other classes. If you haven't, good, you'll learn it today. But feedback systems are a system in which the computer is going to make decisions about, whether it's fuel, timing, EGR, whatever it's going to do, whatever system on the vehicle is going to make a decision based on a series of inputs that it has, temperature, RPM, load, barometric pressure. It's going to take input from those sensors. It's going to make a decision to, how much to inject the fuel. We'll just go with an injector, with fuel injection at this point. It's going to inject some fuel, and then it's going to have, once it injects that fuel, it's going to burn that fuel. And whether it burns it efficiently or inefficiently is going to be detected by, something in the exhaust is going to read that. On a diesel, we don't actually have a feedback like an oxygen sensor on a gas engine, but you might have decisions that are made based on horsepower and other things. Whatever the feedback is for that particular system, that feedback sensor is going to tell the computer, hey, how'd you do? And then the computer's going to say, well, I could do better. I could need to add more fuel. I could leave it alone, or I could take away fuel, and then it'll make a decision, and then it injects it, and then and then that sensor reads it, and back and forth. And that's called a feedback system. And it's just we call that in computer lingo, they call that closed loop. We're closing the loop. It's just constant circle of information coming back to the computer making a decision, and it just goes on and on and on and on. Okay. The reality of it is that these computer systems, within limits, have the ability to take and cover up faulty parts, worn parts, plugged up parts, things like that. We'll just stick with a fuel injector for our example here, but a fuel injector that becomes restricted, say you had something happened to one injector and it kind of got a little bit plugged up. And so that one's not producing the way it should. Okay. And in the diesel, it's going to see that based on the RPM that's turning on that cylinder's producing. So the computer can turn that injector on a little bit longer, and the longer it's on, it's going to produce more. Okay, so it can overcome the restricted injector by just turning it on longer and putting more fuel in the cylinder. Okay, so within limits, it can continue to repair that plugged injector or cover up that worn part. Okay, to the point where and they call this adaptive strategy in a computer system, and that's a whole new subject for advanced drivability and stuff like that. But adaptive strategy is a system in which the computer is going to fill in a whole set of tables and say, hey, I've had to, the last time I ran this engine, I had to, on cylinder 5, I had to turn that injector on longer, and it remembers that. Okay, so it builds that memory up inside there, and it overcomes all those basic worn problems and things like that. Okay, so the computer has that ability to adapt and overcome that stuff. So in a perfect world, this engine could run, well, it could run and nobody'd ever know you had a problem within limits. Okay, and so this thing would just be, a good running vehicle, and the operator might not even know anything's going wrong with his car. And that is our problem. The operator not knowing what's going on with the car. And sometimes the operator doesn't know because sometimes little problems happen slowly. Okay. And the computer kind of compensates for it slowly. And so he doesn't even realize that now he's got, losing horsepower, because it happened to him over a long period of time. But at the end of the day, the operator doesn't even know he's got a problem in his vehicle. And so that's where, got to keep on my notes here. Well, let me give you another example of what the computer can do. Say you had a engine coolant temperature sensor that obviously failed, and was illogical. It was, the engine's warm, the oil temperature's at, 180 degrees, and all of a sudden the coolant temperature is reading minus 40. Well, the computer can logically look at that and say, well, there's no way, with all the other sensors going on in this vehicle, there's no way that that engine coolant is at minus 40 degrees. It would be frozen. Okay. So the computer can ignore that coolant temperature sensor and just use the oil temperature sensor and make all the decisions based on that. Because all it really needs to know is what the temperature is. So is the car running properly? Maybe, maybe not, and not to its peak ability. Okay. So that's where we get into our problems, is it's not quite the peak is what it should be. It's kind of like this. Think about this. If you had a toothache on one side and you were chewing, well, it hurts on the one side. So what would you do? You start chewing on the other side. You get the job done. You chew the food. Everything happens. There's absolutely nothing changes. Everything works good. And everybody around you doesn't even notice that you're chewing on the other side. Then you don't have there's no problem. Your body adapted to the problem. And that's what the computers have the ability to do. Is that good for your body to let the toothache just continue to go on? No, it's not. Same with a car. That's where OBD2 comes into play. There is a problem with a car. We need to deal with it. So the engine might run good enough, but what happens is we start to see decreased fuel economy, and more importantly, we start to see increased emissions. Okay, and that's where OBD2 came into play. OBD stands for onboard diagnostics, and that's what legislation was put into place to limit what the computers could do to try to hide how they run. And to be able to make sure that the cars are running with, I think most of the time, if a system is going to exceed 1.5 times its emission standard, then it's going to flag a fault code. So it's designed to keep things from going undetected. So the OBD2 is a series of monitors that are in the computer, in the car, that are going to monitor the various systems in a diesel engine. We're going to talk about diesel. They're very much like a gas engine, but they're different. They're different ones. But in a diesel, there can be as many as 14 different monitors monitoring the different systems. So, and they're out there looking for problems, making sure that the system operates within a set of standards so that it doesn't have bad gas mileage, but more importantly, so it doesn't pollute. So how does it do it? What's it do? And what's going on? We're going to talk about here, but let's just take the example of the plugged injector. The plugged injector, the computer can sit there and continue within limits, add fuel to that or add on time to that injector to make that injector flow the same amount of fuel as the rest of them so that the car runs even. Well, the OBD2 legislation says that you can only go to a certain point and you're going to turn a check engine light on. It's going to say, hey, we have a problem. I'm having to add more fuel to cylinder 2 in order to get it to operate like cylinder 3 and all the rest of them. So boom, the car may run perfect and nobody notices anything. However, legislation says if you get to this point, we have to turn a check engine light on, going to let the operator know there's a problem. So the guy has to come in and then the technician can repair it. Additionally, beyond the check engine light, it sets codes, freeze frame datas, and a variety of other things we'll kind of talk about today so that it gives the technician an upper hand on being able to pinpoint down as best as they possibly can to a part or a component that's actually failing the car so that we can get these things back on the road. The whole purpose of the whole OBD system is to be able to keep the cars on the road, not polluting. Okay. So enough of my monologue. Let's go through the introduction here. It is dry out and my throat is like ready to die. So bear with me. This may go quick if I completely lose my voice. So I'm just going to introduce some of this stuff and we'll talk about it at length in a little bit here. But the monitors are going to, you can view them in various scan tools and stuff. And they're going to say, either they're going to say incomplete, not ready. They'll say pass, they'll say fail. They'll have a variety of, depending on the manufacturer, most of the Fords are going to say not ready or incomplete. Ours will never say fail, or they'll say okay if they passed. Because what a monitor, well, I don't want to get ahead of myself. We'll talk about it in a second. But here's a good example of a code reader that's going to read it and see. Some of these don't have they're not available to it, but the rest of them are going to say ready. EGR is ready means that it has run the monitor and it's happy with it. If it'll say not ready, or sometime, it hasn't run yet, or if it's okay, it'll say okay. So the OBD2 system also is going to do other things. It's going to turn on the MIL light, which is a malfunction indicator light, also known as the check engine light. So you'll have that. It could turn on the glow plug light. We'll have wrench lights that come on. It's a little shape of a little wrench if it's throttle controls or something like that. It's also responsible for turning on and giving us failures for idle only or reduced power and those kinds of things, depending on, and most of those are going to be related to your after treatment systems. How these systems work, how all the coding systems going to work is you're going to have you're driving down the road, a sensor is out of tolerance somewhere along the line. The first time it's found, it's going to set what they call a pending code. It'll be secret to the driver. The driver will not know it's happening. And he doesn't, he may notice the car running different or may not. Okay. Then the second time he goes out and drives the car on the very next drive cycle, if it happens again, it'll set that as a continuous code in the computer. It's going to set a check engine light, and then so the operator knows he has a problem. But if he continues to drive it and has 3 consecutive drive cycles and it doesn't happen again, it'll turn the check engine light off, but the code will stay in the computer. But if he continues to drive it and it never has another failure again, after about 40 drive cycles, the code will be erased from the computer. So that's not all completely in concrete. That series of events, there's different codes that are failures that maybe a type A, that's really important, and that the first occurrence may turn the check engine light on. So there's variations to that, but that's generally what takes place in a computer when we're going to have some kind of a failure. So, and I kind of alluded this, well, maybe I didn't. So there's 2 approaches that you're going to make anytime you're going to diagnose any car today. You've got a symptom-based approach, or you're going to go an OBD2 based approach. A symptom-based approach is going to be, go back to the example of the fuel injector. If you had a simple car that, the injector wasn't working and it had a misfire, and you went after this car, didn't go into the computer system and or you went back to an old carbureted vehicle or something like that. And just a point of reference, 2 days ago, I had to work on a 1986 6.9 liter diesel I haven't seen in 20 years. And, it's like, oh my gosh, we had to, no computer on it, no nothing. I had to go back and diagnose by symptom. The car ran rough. I had to go and diagnose by the symptom. The symptom was X, it ran rough. What are the things that are going to cause it to run rough? And you have to diagnose it based on a symptom and use that kind of strategy to go to it. Well, the OBD system is a system in which it's going to set codes in the computer and stuff like that. And we are going to read those codes and we're going to diagnose them through a series of pinpoint tests to find the root cause of the problem. Sometimes you're going to have to use both a symptom based and, the code. The code may say something, but it's like, well, that code says this, but I need to, what is the symptom actually happening? And you got to kind of use your head with some of this stuff. And I could talk about it all day long, but until you actually experience it, it won't make a lot of sense to you. And here's the kind of that flow chart of a diagnostic process. Verify the complaint, do a preliminary inspection, make sure that the air cleaner lid isn't left off or something, some big hose left off, something really quick. Do a operational test, make sure, find out how the system's operating. And then we're going to retrieve codes and find out what's going on. Do we have codes? Yes, we have codes. You're going to look for technical service bulletins. We're going to, if there's multiple codes, we're going to establish a priority of which codes are we going to check? Because remember that if you had a series of codes that one said, I had an electrical issue with a fuel injector and I had a lean engine code. Well, why would you go after the lean engine code when you have an injector issue? The injector not working would cause the engine to run lean. So we logically, to the best of our ability, set a priority to the codes that we're looking at. Then we follow the pinpoint test to find the problem. And then get to the place where we know what the problem is, make the repair or the adjustment, and we go and drive it and verify that it's corrected. Okay. And the opposite way would be what we just talked about. If there was no codes, you'd have to go through a symptom-based diagnosis based on symptom, find the root cause of the problem, repair it, and then verify the repair. So some of the things that the OBD2 system affords us, and there's lots of things that and we're going to go through a lot of them, but they give us a lot of real-time data. Okay. Whether it's in, watching PIDs, watching the data that's come across, and we did that a couple of times this semester already. and then looking at the readiness codes and stuff like that. All this data, we can take freeze frame data, and we can take all that data, and by having all that real time data, we can then make decisions about what it's going to take to repair these cars. And I'm sorry that this has a GM label on it. So after we're done fixing them, we're going to erase the fault codes. We can get it all cleared out, and we're going to go through a drive cycles, which we'll talk about here in a little while, to verify that the repair was successful. Okay. Okay. So let's take a step back and talk about the OBD2 requirements for diesel engines. This is the legislation that's put out, and it's not complete, but this is some of the legislation that's put out to say, okay, what is the requirements that diesel engines have to have, whether it's a Chevy, a Ford, a Dodge, a Mercedes, whatever it is. Okay. And gas engines have their list as well. But they must have a malfunction indicator lamp in the driver's view. If we went back to the early days, back in the early 80s, Ford and Chevy both had computer systems. Chevys turned their check engine light on and they stayed on. If they had a problem, the light stayed on. Ford was a little smarter in the beginning. If the problem was there, the light came on. If the problem was gone, the light went out. It may have stored the code, but the light didn't stay on. Well, they got away with a lot of not having to make a lot of warranty repairs because the light went out, and it wasn't as big a deal as a customer with the light all the way on. Well, the government figured that out in a hurry and said, no, if there's a problem and it turns it, if it's a problem, it's going to set a code, you're going to turn the check engine light on and leave it on. So it's important that, part of the system is that the driver or the operator knows that a check engine light is on, that he has a problem. Okay. There has to be a standardized 16-pin diagnostic connector within the driver's area. Okay. Sometimes they're a little out of the driver's area, but they have to be within a certain area of the driver. Not that the driver does anything with it, but it's just so that if, you're an independent shop, no matter what manufacturer is going to roll into your store, you can know basically somewhere around the driver's foot area, there's going to be a connector that you can plug into and test, and you don't have to go searching for it. There's standardization of a series of diagnostic fault codes across all manufacturers. We'll cover that here in just a minute. Standardized network communications. In other words, the network talking to the scan tools is all going to be standardized so that, you don't have to have 10 different scan tools to talk to 10 different cars. You can buy, a Snap-on Solus, or there's some other, aftermarket ones you can plug in and talk and get all this data that I can get out of my Ford program off of any vehicle. Now, my Ford program only works on Fords. I can't go to someplace else, but the independent stuff or the generic stuff will work on everything. Have to be able to display freeze frame data for fault codes, and we'll talk about what freeze frame data is here in a minute. This is a biggie: standardization of names and abbreviations of components in a system. In the early days, engine coolant temperature sensors were called, what did we used to call them? It's old. Well, anyway, Ford had a name, Chevy had a name, everybody had a name. Okay. So nobody knew what, you had to guess what somebody was talking about when they said a name, because they were never really simple. But the legislation came out and said engine coolant temperature sensor is going to be an engine coolant temperature sensor no matter who's making it. Same with intake air temperatures, fuel injectors, exhaust sensors, all, whatever it is, everybody's going to call it the same thing so that an independent can get a hold of this thing and know what he's fixing, and he doesn't have to, guess at anything. They even went so far with all that we don't have alternators anymore. They call them generators because they wanted to keep them. They just wanted to have very generic across the board. They have to have the monitoring systems, which is what we're going to talk about at length here in a little bit, to be able to verify proper operation. Same thing. All that's just all about the monitoring systems. So this is the diagnostic data link connector. If you look under the dash of any car built since 1996, and we even introduced it in 1994 on the Mustang, but every one of them are going to have this exact same connector in there, and the pin placement on these is going to be the same. This pin 16 is going to be your power, and I believe the ground, where is the ground? Ground is 5, somewhere up in here. Signal ground, and then 4 is chassis ground. So these are going to be your grounds, and then 4 and 16 are your CAN network, and 11 and 3 are, I think, a low speed CAN. And some of the stuff changes through the years, but depending on, if it's a CAN network or some of the early networks. But at the end of the day, these things all have to be standardized. Now there's some pins that are open in here that are not standardized by the government, and the manufacturers can put some different, like it says here, 11, 12, 13, and 8 and 3 and 1 are at the manufacturer's discretion. So they leave those so that we can put different CAN networks inside those, so we can test them with our scan tool. But this is the connector of choice that you will find under every dashboard. Okay, so how does a network work, and how does all this work? And not going to get really crazy about networks, because if you get into the drivability classes, gas drivability classes, you will get this ad nauseum. But just generically, just to give you an idea of how it works, is it is a network line like phone lines. So that, I mean, this is a really good picture. You got, 4 different modules here, all talking to each other. Okay. All on a twisted pair of wires, one twisted pair of wires. Okay. And so you have this is a picture of a high-speed CAN network. This is 6 and 14. And all these things are all connected to this twisted pair of wires, and they're all going to talk across this network. Each module is going to talk one at a time, and they're going to set priorities. Who's getting to talk, however one's talking, one's receiving the message, and it's sharing. What they're going to do with this, and what's important about this, is it cuts back on the need for, if I have, some of the early stuff used to have, a vehicle speed sensor for the transmission control module, a vehicle speed sensor for the engine module, and so in wiring all over the car, and or you had a vehicle speed sensor and it had wires that ran to everything, and so you had wires everywhere, miles and miles of wires. Well, that is inefficient, it's heavy, and what we can do is we have this network in here. So now the transmission control module, or actually probably the ABS module, is going to get vehicle wheel speed information. So it gets the information about how fast the car is going. It's going to share that information across the network with the transmission control module and the PCM somewhere, the engine control module over here. And it's going to share that information. Okay. Then then these things will make that decision based on that, and so on and so forth. So you're going to have all the information, whatever the information is, engine coolant temperature, vehicle speed, engine RPM, all that stuff, everything gets shared back and forth across these modules. And there's lots of them. I mean, there can be, I think some of our hybrids are running 14 or plus modules on them, and they're all talking to each other, but they're not all talking on the same network. I think, yeah, they're not all going to talk on the same network. So you're going to have, say, this particular one is going to be on this network and this network over here. And so all these modules might need to share information across network lines, so that we have these, what we call a gateway module. So this thing sits in here, and all these modules sharing this information, it can go through the gateway and then share it to another network. So there's all kinds of different networks all over the car, and they all talking to each other. And that's what all that data link stuff is. So the new stuff that's out there is called CAN networks, which is controller area network. It's not actually all that new. It's probably darn close to 20 years old now, I guess. but it's the newest stuff, and there's even some faster stuff out there because we have CAN 1, 2, and 3, and lots of different CAN networks out there. But the CAN networks, they're just high speed. There's high speed, medium speed, and low speed CAN networks, and they doing what I just said. They're just sharing information across each other. They're sharing it with a bunch of, it's just serial communication with zeros and ones, just like a computer. It's all it is. It's not, we're not talking about it sending out an analog signal or anything like that. It's strictly a sharing digital information across the network. Here's just a picture of an example of one module's accepting, checking, and receiving the data. Okay. The other one's providing data and sending it, and all the what's happening back and forth through the different modules. And this all happens pretty quick. Okay, so what you're going to see on these, not all modules are going to be a twisted pair. There's some networks that are just a single wire, but mostly all the CAN networks and all the big important stuff is a twisted pair of wires, and one of them's going to have a low and one's going to have high, and it's going to be alternating. When one's high, one's low. When one's low, one's high. So you're just going to have this alternating voltage back and forth, and you can see this in an oscilloscope. Okay, and if we're watching a CAN network, we're just tied into that on an oscilloscope. This is what it looks like: a high and a low, and a high and a low. And we're not going to get into network diagnostics here, but I want you to know that it's there. Okay, so we're going to shift our gears and talk about fault codes. Fault codes are used to bring us down, hopefully, to the closest possible point of the failure. Now, some fault codes are very generic and are, only informational. Lots of, informational codes out there that you just drive you crazy. But most of the codes are trying to get you down to, hey, the problem lies here, go find it here. And that's where we have our, we have standardized codes that are generic, that are legislated, and then there's going to be diagnostic fault codes that are manufacturer specific, so that the manufacturer has the ability to, hey, I'm going to put a whole bunch of codes out there so we can diagnose our cars right to the point of the problem. So when we pull codes up, has anybody ever pulled codes on a car? Crystal, have you did we do any of that last semester?
No.
Okay. Did we talk about this at all last semester at the gas engine class?
Yeah. A little bit.
Okay. So, so codes are going to come up in all OBD codes since 1996 are going to come up in this format. It's going to be a letter with a digit, 4 digits. The digits can be numbers, and then probably in 03 they started introducing letters within those digits, so it kind of gets all murky. But the first digit is going to determine the system that it's involved with, whether it's a B for body, C for chassis, P for powertrain, which will include transmission, or U for network codes. The next digit is going to be 0 is going to be a generic code, like a those, when I say generic, those are codes that the legislation says, hey, you have to monitor these systems. This is the code for that. This says, hey, these are all generic across the board. So if we'll just take this for example, this P0304 is a cylinder 4 misfire. Okay. This, because it's generic, that O will know that no matter if this is a Dodge, a Aston Martin, or a Lamborghini, if it has a P0304, we know that it's a cylinder 4 misfire across the board. Okay. But if it was a manufacturer code, they can be they'll put a 1 here. Most of our manufacturer codes are either going to be a 1 or a 2. And I've never seen, they supposedly have a 3 out there. I've never seen a 3. But we'll have a 1 if it was ours, and it'd be like a P. I could give you an example of a P 1131. 1131. I think it's going to be like a manufacturer specific code that says that the right hand O2 sensor is lean, I think. And that doesn't, that 1131, if you went to Dodge and looked up a P1131, it would not mean the same thing. Okay. So you have to be careful with that. The 1 changes that. The 1 or the 2 there changes that. The 3, the third digit over is going to describe the subsystem, whether it's 1 is fuel and air, 2 is fuel and air, 3 is always going to be the ignition system or some kind of an engine misfire. 4 is going to be auxiliary emissions control systems like secondary air, EGR, that kind of stuff. 5 is going to be vehicle speed controls and idle controls and stuff like that. 6 is always computer control problems, usually maybe voltage issues, but most of the time some kind of a computer memory failure inside the computer itself. And then 7s and 8s are going to be transmission control things. So you get familiar with these, you'll be able to, immediately, pull a code and say, it's got a P17 something. It's like, well, okay, a P1744. Okay, that's a torque converter problem. Because I see the 7, I can say, stop. I'm not dealing with it. It goes to the transmission department and get rid of it. Okay. You can immediately, get to know this stuff and you'll be able to do that. Okay. And then the last 2 numbers are going to be specific to the identifier, what's going on. So on this example, the P0304, we know that that's a cylinder 4 engine misfire. Be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, to a 10 cylinder. It's going to, do that. Or P03, 1, 1, P0311, I think P0311 is with a 1 there, and then the 1 takes us to the an actual coil problem. So you kind of get to understand what these things are, and you could pinpoint right down to their problem. But you don't have to memorize this stuff, because once you take the code, you can go into the workshop manual or into the pinpoint test, find the pinpoint test, and it'll walk you right through, a series of things to find out what's going on with it. So we just covered that. We covered that. Okay. So, as we talked about priority codes, we talked about placing priorities on codes. Well, we can do that, but the computer also does the same thing. It sets priorities as well, as far as when it's going to turn a check engine light on and things of that nature. And we'll have type A, B, and C misfire or codes. A type A misfire or a type A code is a code that says, hey, the problem that's happening right now is going to damage a catalytic converter. That's a type A misfire. Okay. So if we had raw fuel going into the exhaust on a gas engine or something like that because of a misfire, and we have some sort of a misfire. If we have a misfire, we're not burning the gas. So raw gas is going in the tailpipe. It's going to hurt the catalytic converter. That's considered type A misfire, and that will flash the check engine light and leave the light on first try. Okay. It doesn't have to do it on the second cycle. Type Bs are same thing. They're critical, but not as critical as a type A. And type Cs are not critical at all. Something like intake air temperatures not reading right, or air shutters or something on the shutter controls or something aren't working right. Something really minor that's not going to cause a bunch of emission problems. Would be considered type Cs.
Would an exhaust leak be considered a type C?
Well, it would all depends on how it how it picked up the exhaust leak. Okay. Cause, the exhaust leak is it's not going to be a code that's going to come and say, hey, you have an exhaust leak. What you're going to find is a code that says, hey, and now keep in mind, this is depending on where the exhaust leak is, but we have problems. You'll have problems on some of these where the cat monitor sits on the backside of the cat, and then where it sits on the backside of the cat, maybe there's a flange on the back that goes back to the exhaust. Well, if that flange leaks right there, as the exhaust comes in there, it can swirl fresh air in there. So now all of a sudden that cat monitor's seeing fresh air, and it gives weird sets of codes. It could see that as, hey, the cat monitor's not working quite right, but it's not a big deal. Or it could see it as, hey, I got air coming through this thing that I shouldn't have, and I got a potential cat failure. So it could, depending on where that exhaust leak is, it's going to be your computer's going to pick it up in a performance sense instead of it's not going to be like a circuit fault. It's going to be something's not performing quite right. And based on how it picks it up, it's going to decide whether it's a type B or a type C. I don't think it would ever pick that up as a type A, because type A's are going to be, some kind of an immediate failure that's could cause a cat failure, a misfire. I can't think of any others. I don't know of any other type A faults other than misfires. I think everything else would be a B or a C. I could be wrong on that, but as far as I know, that a type A is something that's going to hurt the cat. Does that make sense?
Yeah, that does. Thank you.
Well, this PowerPoint here says that scanners, and this comes out of the class, scanners report fault codes in priority of their effect on emissions. And I don't know that that's true. I don't deal with a lot of aftermarket scan tools. So I don't know how they're bringing it up, but Fords don't bring them up like that at all. It's not, ours aren't laid out in some sort of a particular order. You need to just, you need to decide what order is important, not the scan tool. And this is always important, is just consult service literature to determine the sequence or priority of diagnosing a code. And one of the things, I would say 90% of the time you're going to come in with one code, but you're going to have that time where you've got, you might have 3 or 4 codes, or there's times you open up a car or you pull codes on a car, and there are, 20 codes in this thing. You're like, okay, what am I looking at? Or especially if they're, all hard faults, which a hard fault is a code that's happening like right now. And you got to decide, you're looking at this thing, what in the world where do I start? And you can get, I'll just give you my 2 cents as a mechanic. And as you look into your mechanic world moving forward, you just have to make a decision. You have to decide, look at the codes, look at them logically, say, always go after circuit fault codes before you look at performance codes, but decide, okay, I'm going to go look at this code and I'm going to chase it down, because 90% of the time, if you got, 20 codes in there, it's one thing went wrong. It caused it all. And it could simply be a blown fuse because of a shorted wire. And you could sit there and spin your head all day long going, where are I going to go here? Pick one code and chase it. If chasing that code for 10, 15 minutes says I'm going nowhere fast, leave that code alone and find another one and go after it and find the root cause. And you'll find that if you just focus in and find one of those codes, because something caused that code just like it caused the rest of them, go in and try to find that. And you may find that one thing fixed the whole thing, or you might have a series of, okay, is this, these are related. These are in, these ones here are related and these ones are related, but they're not related to each other. So, okay, you may have two different things going on, and it's possible, it depends, especially if a rat got in that engine, a rat can go in there and he can have a field day, so, use your head, I guess is what I'm trying to say. All right, so let's talk about what freeze frame data is. So freeze frame data is data this is part of OBD2. Legislation says that the vehicles have to capture data when a fault occurred. Okay, so we're driving down the road and a fault happened. Some faults may be a wire went open or something like that, or something may be that, hey, my NOx sensor went out of spec for more than 15 seconds. Okay, boom, we're going to set freeze frame data when it sets that code. Okay, so the purpose of freeze frame data isn't for you to be able to look at this data and go, okay, I see that this sensor was out of spec and we're going to change that sensor. Okay, because that don't work. Freeze frame data, with very rare exceptions, gives you any data valuable to diagnosing your vehicle outside of when and what was taking place when it happened. Okay, so if you look at this vehicle here, that whatever was going on with this car, it looked like a charge air cooler inefficiency. Okay, in other words, we weren't getting a temperature drop across the charge air cooler like we thought we should. Okay, what was happening? Okay, the engine was at 1700 RPM. Vehicle speed was 0 miles an hour. Load was at 14%. Okay, so after we make our repair, find our problem and make our repair, we can, or to try to find our problem, we want to look and find out what was happening. What were the conditions that around when this was caused? Well, obviously it was, a little bit of high RPM, no speed at all, zero speed, with no load. Okay. So why would we drive the car down the road looking for the problem if it happens at idle? The same way, if the car came in with some kind of a code and it was set at 60 miles an hour on a hot engine under a heavy load, well, we want to be able to duplicate that problem. We have to go duplicate what was happening at the time it set that fault. Okay, we could sit and idle it all day long in our stall and never get to do it. But the reason for freeze frame data is that we can find out what was taking place when the fault occurred. Okay, so we can use that to help us diagnose the problem, but we can also use it to help us verify the repair. Okay, so now we found a problem. We think we've found the problem. We fixed the problem. We want to take it out and drive it. Okay, if it set the code at 60 miles an hour under a heavy load, and we just drive it around the block thinking that we repaired the car, do we really know that we repaired the car? Not at all, because we didn't put the car back in the same situation that it was in when it had a failure. Okay, so that's why we use freeze frame data. Again, freeze frame data is not to capture the data of what was wrong with that part. Okay, a couple of rare exceptions might be exhaust temperature sensors. If you had a big failure on an exhaust temperature sensor, it may show you that sensor was the problem, that one was way out of whack or something like that, but generally not. We just talked about all of that. Okay, so some of the strategies of how OBD2 works is it's going to, there's inside the, where did I go? Inside the computer, there's going to be a voltage reference is going to be set across a signal, and it's actually going to look for a voltage drop across the sensor. And the computer's going to do that. It's called comprehensive monitoring, and it's going to monitor all the hardwire systems in the car, looking for, well, not say all, but all the critical hardwire systems in the car. It's looking for voltage drops across these sensors. Okay, if something happens and this wire goes open right here or shorts to ground or something like that, the computer can actually see that in that voltage drop, and it's going to flag a code. Okay, so it's what it's looking for is, hey, this is this normal operating range. All of a sudden here we're out of range or we're low, and it's going to flag a code. Keep in mind that this thing, look at the normal operating range of this sensor. Okay, this sensor, when it's engine's hot, the voltage is going to be really low, and when the engine's cold, it's going to be really high. However, something could fail in here, maybe some corrosion or something like that, where this thing could fail and be at still within the normal operating range, but not be right. Okay, so the computer can't see that. It's kind of blind when it has a failure within range. So keep that in mind as well. Okay, the other thing it's going to do is going to do rationality checks, and rationality checks are going to say, hey, on this example here, there are 3 throttle position sensors on here. Remember the Lexus that killed all the people in Santee because the throttle stuck on him and he just drove off the edge of the freeway and killed his whole family and everything? Well, that car, its rationale, it didn't have some of that early production throttle sensor stuff didn't have rationality checks to say, hey, this thing shouldn't be at wide open throttle and the brakes are on and all these different things going on. So what they've built into all these systems is all these cars have 1 or 2 throttle position sensors built within one throttle. Okay, this is the accelerator pedal, and it's just a sensor. And this thing is either going, it's one's going to have dropping voltage, the other 2 are going to have climbing voltages as it opens, but it's looking at them logically. Okay, so it knows that if this one's tracking here, this one should track here, and then this one should track here. So it knows exactly what's happening. And if one of them's off, it's going to say, hey, something ain't right. And so it's going to set a code, probably going to idle only, and it's going to say, hey, this is irrational. Okay. The other thing, remember I gave you the example of the engine coolant temperature sensor that all of a sudden reads minus 40 degrees, and the engine coolant oil temperature is reading 180. Okay, it knows, it's going to look at that and say, this is irrational. This doesn't work. Okay, so it's called a rationality check, and it's going to say, hey, this isn't right. So it's going to ignore what it's going to do is it's going to look at other systems and other operating things that's going on and say, hey, I'm going to ignore that engine coolant temperature sensor because it's not rational. It's not logical that it would be minus 40 when everything else, I got a running engine. I got an engine that's got, this kind of exhaust temperatures and this and that. It's not logical that it would be, so it ignores it. Okay. Okay, so let's shift gears here and talk about the monitors that are in the system and the readiness status of them. Okay. So there are a series of, like we talked about, there's up to 14 different monitors in the vehicle. And depending on the monitor, some of them are what we call continuous monitors. They're going to run all the time. The ones that are checking circuits and stuff like that are going to run constantly. Misfire monitor is going to run as quickly as possible so that we can determine whether this thing's got any misfires on it. Others might have to go through a whole rigmarole in order to try to monitor its system. Okay. But what these monitors are to do is to just do that. They're monitoring the system to find out, how how the system is operating. And then it's going to either report a pass, a fail, or a have not run yet. And this is part of the, if you ever try to get your car smogged and something, you had a repair or something, they're going to say, hey, your monitors aren't clear. You got to drive the car to get it to clear its monitors. And what happens is you're driving the vehicle. It's going to let's just give an example on a gas engine. You're going to drive it. It's going to make sure the oxygen sensors are going to work. It's going to make sure it's going to actually go through the evap system. It's going to pull a vacuum on the gas tank, make sure that the gas tank doesn't have a leak, and run that monitor. And we're going to do the same thing with the diesel engine. It's going to go through a series of tests depending on what test it is. Let's just give you an example. I actually have a slide at the very end where a video that I made today of a monitor check to check the condition of the NOx 11 sensor to make sure that the rationale of that sensor is correct. And what it does is you're driving down the road once per drive cycle. When you come to a stop with the car in gear at an idle, it's going to turn the EGR valve off, watch the NOx levels go up, because remember, when we turn off the EGR valve, engine's going to create NOx, and it's going to watch that. If we see that rise like it should, then it's going to set the numbers and say, hey, it's good, and that monitor clears. If it shuts the EGR valve off and the NOx reading doesn't go up, well, it's going to flag it as a bad sensor. But when we get to that slide, I'll kind of explain a little bit more about what it can be. So we have to look at things kind of logically. However, all these sensor monitors are going to, some of them are going to be like that one. It's going to actually turn a valve off and see what happens. Other ones are just going to, if all the parameters are set, the things at the right temperature, you're at the right road speed, and everything's perfect, it's going to look at a sensor, and say, okay, is everything reading properly? Boom, it's going to work. Some of them, different monitors are going to do different things to run themselves. And like I said, they're strictly a monitoring system to make sure the car is working properly. So let me make sure I'm covering everything here. Okay, like I said, there's 14 major systems required by the EPA to diagnose these diesel engines. So we're just going to cover a few of them and what they are going to do. Fuel system monitor, it's going to evaluate fuel injection pressures, the quantity that's going in. Remember I said if we have a plugged injector and we are, making adjustments, and all of a sudden it's like, hey, I'm out of spec on this thing. It's like, okay. Multiple fuel event performance. Okay. This week I have a transit in there that actually set a code that says it can't enable the pilot injection. Remember when we were talking about common rail injection, pilot injection was when it would fire an injector before the main injection, so that it would start the flame propagation across the top of the piston, so that when they put the main injection in there, you wouldn't get that cracking noise. The computer could actually tell me that, hey, I can't enable that system. So it's like, okay, great. But it has a monitor to be able to monitor that. It monitors its timing. It monitors its closed loop feedback controls. Okay, so that's what it's doing with the fuel system. They got the misfire monitoring. What happened to misfire monitoring? Well, we monitor misfiring. I don't know what happened to my slide. EGR, we're going to measure the rate of flow, response rate, whether it's being cooled properly. When we open up when we hit the bypass valve, are we going to send the EGR through the cooler? Is it cooling it down properly? Is the cooler actually working? Remember in that freeze frame picture, we said that there was a code that said that PO26A, that same cooling system that cools the charge air cooler system, is also cooling the EGR. So is it all working? Are all the feedback controls working? So we're monitoring these things to see how it works. Boost control the same way. Is it got an overboost or an underboost? Wastegate operation. Is the turbocharger responding quickly? Is the charger undercooling? That's what that other code was, that PO26A. Cold start emissions. We monitor the glow plugs. And some of these things have a heater in the intake air, but we don't use those. But, are the glow plug systems working? We check engine cooling system, crankcase ventilation systems, comprehensive component. That's monitoring all of the input and output signals, make sure all the wiring is good on everything. We measure the aftermarket treatments for NOx, for make sure the oxidation catalyst is working, make sure that, remember we have the particulate matter traps, the sensors in there to make sure that we don't have particulate matter going out the tailpipe, and we want to make sure we don't have NOx going out the tailpipe. So we're monitoring all of those things. We monitor the DPF system. If we're having to regen the thing too much, if it's plugging up constantly, we know we've got a problem with that thing. We monitor to make sure it's gone through a completion, make sure that it's going all the way through cleaning the exhaust. It's monitoring it with pressures and stuff to make sure that somebody didn't take it out. Because, you could just plug it out, or, put a straight pipe through there. Okay. And so the system knows if there's, if it's missing. If it's engine's cold or something's going on, we set codes that say, hey, we can't make regeneration happen because I can't make the heat across the oxidation catalyst. Remember, we have a sensor before and after the oxidation catalyst. We monitor the temperatures of those things. Once we're hydrocarbon dosing that exhaust, we should see at least a 200-degree rise in temperature across the DOC in order to cook off the DPF. If we don't see that, that 200-degree rise, well, it flags a code and stops regeneration. I want to show you, where did I go? I'm backwards here. Boom, boom, boom. So see if let me see if I can make this make sense. So I think that one's not going to make sense. Okay, here's an example of what's happening. So when we're monitoring exhaust, okay, so we're going to, in fact, this is exactly the picture that I'm going to show you at the end here. So we turn off the EGR, we see the NOx levels are here, and boom, the NOx levels rise. Okay, we end the test, that turns the EGR back on, and boom, comes all back on here. Okay. So that's an example of an intrusive test that the system is cycling the EGR to make it happen. Other tests may be continuous, that it's just constantly monitoring something. And if it sees the levels go above a certain, like a NOx, when it's monitoring the SCR, it's driving down the road and it sees those NOx levels go above for more than 15 seconds. It says, boom, I'm going to set a code for you. So we talked about this a little bit. So you have the functionality of things to make sure that are the systems actually functioning. We have rationality or plausibility monitoring, which is what we talked about. Is this rational or is it plausible? Is it even plausible that we could have, minus 40 degrees and 180 degrees out of two sensors in the same engine. No, it's not rational. It's not even plausible. Is it plausible? Is it plausible for us to have engine coolant at 130 and the oil at 180? Yes, it's plausible. Okay. So then so then it has to make other decisions. I've got a problem. It's plausible, but it may not be likely. So there's just a piles of codes out there that'll come into play in that kind of situation. But it'll also say we could get codes that are going to give us let's see some examples of some codes that say, hey, I'm reading my NOx in my tailpipe is reading higher than the NOx coming into my exhaust. Okay. That would mean that you're making NOx in the exhaust. That's another thing that's not plausible. Okay. So so in those situations, it's going to say, hey, there's a rationale or a plausibility between these two sensors. You got an issue. And so now you got to go, it can't tell you is this one reading high or is this one reading low? So we got to go back in, and that's when we got to go through a set of diagnostics to try to find that. Okay. And we talked about continuous and non-continuous monitoring. Continuous means that it's constantly monitoring something. The non-continuous is that maybe, like I said, that exhausts only once every drive cycle does it look at that. It's not something that's looking at it all the time. So monitoring enabling criteria, and this is something that will always be very important to you. If you get into this world and start working on these cars, understanding the criteria that is going to enable the monitors to run is so critical for you. And it's one of the things that frustrates me the most. Like I told you the other day, I have a truck that he's got probably 4,000 miles on it still right now, and it still has not run a particular monitor that we're trying to run in order to clear, or in order to know that we have fixed the car. So he's driving around, because what happened was he came in with a complaint. We made a repair, and we were unable to verify the repair, but he needed it back. So we gave it back to him. He drove it for pert near a month before in a month and about 4,000 miles. And it came back with a check engine light on with the same code. It's like, okay, well, did something happen in 4,000 miles that it came back with the same code? But so we went in and did some investigating and made it yet another repair and said, okay, let's try to clear this thing. Let's try to find out. Let's try to run this monitor and make sure that it's fixed. Well, we've been unable to get that monitor to run. And I've been unable to figure out what the criteria are that enable that thing to run. Something isn't right. There's something likely wrong with the car somewhere that says I want my exhaust temperatures to be here. I want all these things to be in the place, whether it's vehicle speed, temperatures, pressures, whatever they are. Everything needs to be in place for me to run this. Because just last week, I did the exact same repair on a vehicle, and I drove it 10 miles and I ran that monitor, and I knew I had fixed the car. I've been unable to even get the people from Ford to be able to tell me, what am I looking for what is the criteria that's happening? Something is preventing this thing from doing that. And that's pretty off the wall. But if you can figure out and understand the criteria, what it's going to take to run these monitors, you can know and quickly know that you have repaired your vehicles. Examples of that, I could give you gas engine examples. We have to clear those on gas engines a lot more often. But, in order to clear the catalyst monitor, you have to drive the vehicle in town driving at, you want to do at least 5 40 to 60 mile an hour cruises within a 10-minute period. In other words, you're going to go up to 40, 45, 50 miles an hour, stop. Do that, 5 times within 10 minutes. Okay. And it'll run that monitor. If you know how to do that, it's all quick. You could drive that car for hours up on the freeway and never get it to do that because you didn't get the enabling criteria. Same way with any of those monitors. You've got to find out what it's going to take to run that monitor, and then you can get it to do it. And it doesn't, you may want to run and get all the monitors to clear on a vehicle, but really, if a vehicle comes in with a complaint that was associated with a monitor, we really just want to run that monitor. We can clear that monitor, we know that we have fixed the car. If it runs a monitor, because if it runs a monitor and still sees a problem, it's going to flag the code and you're going to go fix the car. But if you run the monitor and it says, hey, I passed, call it good. Okay. Yeah. This is important. Technicians should study OEM service literature when diagnosing the root cause of a DTC. I could yap at you all day long about all this stuff. At the end of the day, when you are checking a car out and you get a code, read up on the code. What does the code say? It doesn't say, I have a P0304 misfire code. I need to go in and change the plug and the coil and the injector. Because chances are, if you change the plug and the coil and the injector, you're probably going to fix the car. But the reality of it is, it may just be the injector that caused your problem, or it may just be the plug. It's not going to be all 3 things. Okay, so that's where you get an understanding of what it is, so you can get to the root cause and fix it right. Okay. Studying how the manufacturer has configured the monitor to operate is essential, and I will challenge you, especially with the diesel things, that it is hard to understand what all it is. Ford actually publishes the stuff that is actually comes from the government. It's in our page. In fact, when we're done here, I'll take you there and show you, and I'll just take you through a couple of them and show you all the criteria that Ford, or that the manufacturer has to follow from the government to make all this stuff happen. And it's pretty heady stuff. Misfire detection monitor. We want to know, how it happens. This is where that slide went. The misfire detection, it's very simple. When a engine misfires, we can sit there and watch the RPM on an oscilloscope. We can watch it really smooth. But as this one here drops, because we now have a misfire, it's going to pick that up. And that's all that misfire monitor is doing, is watching the RPM from cylinder to cylinder to see how that's working. And when it sees multiple events like that, it's going to flag a code. And it's just only monitoring the crankshaft position sensor. I think I covered all this stuff. So the exhaust sensor is only going to, most of the time, our exhaust is, if we have exhaust coming in the engine and we have air coming in the engine, what they're going to do is they're going to monitor the mass airflow sensor. And if we open up the EGR, we should see a less air coming in if the same amount of air is going in the engine and we open up an EGR, we should have less coming in the intake and more, and then air coming in the EGR. And that's going to, you're going to see that in a drop in the mass airflow sensor. So the mass airflow sensor is going to be our main sensor that's going to tell us whether the EGR is actually working or not working. And there could be pressure sensors, but usually it's always going to be mass airflow. we've covered all of this. I'm going to bore you to death here. I want to show you. I'm going to show you this. I'm going to show you some OBD2 stuff. Okay, so this is a vehicle. Sorry, I had the radio on for a second. There we go. Got rid of the radio. Okay, I'm just booting up on a car here. Here we go. So what we're going to look at here, I'm going to get it up here and freeze frame it. We're looking at OBD2 results. Let me bring it up here. Okay. So when this thing runs monitors, it's going to set this information in. This is all a generic OBD2 mode 6 data. This is all legislated stuff that all this stuff gets placed into, and it's most of it's a lot of mumbo jumbo, and it's exceedingly heady and hard to read and everything. But when you're looking for especially specific monitors, and some of them are going to call you out to go in here and look. So this particular one here, NOx sensor control high, and that's what we were looking for on this particular vehicle. And I made a repair. The vehicle came in, and the minimum number and the maximum number are going to, the maximum is always going to stay the same. I'm not sure what affects why it changes the minimum number, but these are the numbers that we got to work between. And the car came in with a reading that was at 306 for a minimum and 1500 for maximum. And the value that it read was 353. Okay. Well, my spec was that this number needed to be a minimum of 50 parts per million above this one here. So I was actually at about 40. No, I think it was at 40 parts per million or 50 parts per million instead of 53. And I was like, okay, I knew I was like right on the borderline. So I had an remember that picture before us? It said when we turn the EGR valve off, the NOx should go up and then stay up for a period of time. And then when we turn the EGR valve back on, it come back down. Okay. If the NOx does not go up, it automatically sets a code that says my sensor was bad. It's not reading the NOx coming in. Okay. But here's another scenario. What if the EGR valve is leaking? Okay. And so it's leaking already. And when I turn the EGR valve off, it's still leaking EGR gas into the engine. Okay. So my NOx does not go up. It stays relatively low. Okay. And so now the computer thinks I'm just not seeing the NOx, but in reality, I have an EGR valve that is leaking exhaust and giving the sensor a false reading, and the computer's seeing it wrong. Does that make sense? Or did I lose you on that? Yeah. Okay. So we have to take everything. You can't just go hucking parts, and all of us do. We, especially at first, we may huck a part. Well, that didn't fix it. We have to go find out what's actually going on. So I went in and I found, because it's just experience, because I've hucked plenty of parts at one of these before, trying to figure out what in the world's happening with these things. But experience says, okay, I have a valve that's leaking. So I can pull the EGR valve off, and sure enough, it's leaking. I put a new valve on it, and I go and drive it. And what the criteria to set this monitor is that once per drive cycle, in other words, every time I cycle key on and drive it, one time, if all the planets line up and I'm sitting at a stop in gear at idle for a given period of time, it's going to turn the EGR valve off. And it's going to watch that and do that. Okay. One time, every time I drive it. And boom, when I turned off my EGR valve, I went up to 457 parts per million. Okay. So I'm clearly over 50 parts per million. Above that, I could know with a great level of confidence that I fixed this vehicle and it will not come back, because I ran the monitor, I did the drive cycle, and did what the computer's looking for to make sure that I fixed that. Does that make sense? Okay. So I'll give you another one that's just in here that we use a lot is this Knox catalyst, this bottom one here. Oh, it only picked up didn't pick it all the way up. It only picked up the Knox cat conversion efficiency down the bottom. Okay. That particular number down there is telling me that my Knox, that my SCR, my selective catalyst efficiency vector, or the SCR is working properly, that it set that number. I would actually like to see that 7.5 number in the bottom there. I'd actually like to see that usually closer to 0.9. But 0.75 is quite sufficient that I know that the exhaust is all working properly on this vehicle. And there's other things in here that we can pick out, but I think they're lower on the screen. But in the same way, we can actually watch how many misfire counts further down on the screen. They're going to be misfires per cylinder. We can actually see how many misfires took place in the last drive cycle and all that kind of stuff. And all this stuff is being monitored by the OBD2 system. And the results are placed right here. I don't think I did anything else to this. Okay, so let me do this. Let me find. Let me do this. Let me do this. Let me do this. And then I can go. Now, why didn't it pick that up? Come on, baby. I'll go here, here, here. Do you see how come I'm not picking up? Oh, no, how come you guys see? I'm not, for some reason, I'm not seeing, trying to bring up my Google Chrome here. Come on. Do you see Chrome on there? There it is. Oh, you guys probably can't see what I'm looking at, can you? All right. Let's find our canvas here. No, I don't want that. I want canvas anyway. I wanted this. And now I shoot, I'm going the wrong direction here. All right, here we go. I'm going to bring you up another share. Here we go. Oh my. All right. So this is all the literature that's out there on this. So we just pick up let's grab a 14 diesel. And this is all the OBD2 literature that's out there of what's in here. And let's try to find, I think if we do Control F, let's try to find a P207F. Okay. So now we want to find these two codes are two that really beat us up all the time. And you need to try to figure out, okay, monitor execution. Okay, 20E, once per driving cycle. Okay, the PO207F is continuously. So it's going to tell you those are, how often are these going to test themselves? Okay, these are the sensors that says, okay, NOx, all these sensors here all have to be okay before it's going to run. Okay. Well, when we say okay, that's one of the things that frustrates me. I've been trying to chase down a P20EE on a 19, and okay, all these are okay. Well, I look at them and they're okay, but what does okay mean? So, is it's okay, but is it way out of spec? I don't know. But it's going to tell you the duration of it is okay. It's 20E. It's going to be for 1 minute. It's going to run this thing. What is the criteria? I don't fully know all the way. But as it goes through, it's going to tell you, it's going to have all this information that it's trying to read when it's reading it. Okay. And it's like, okay. And I told you that some of the stuff is like really heady and you're trying to understand, what's a torque transience, what are all these things? I don't even know, but all this stuff, but this is what all that monitoring system does. But anything you ever need to know about, you can go to this book and try to understand it. And sometimes it's, you got to read it a couple of times and okay, I see what they're trying to say and what they're looking for. But the 20EE is it's looking for, how is a catalyst actually reducing the NOx? The P207F on the early system, that's how they used to measure how good the the exhaust fluid was in the system. Rather than testing it now, we test it with an actual sensor. But I'm just trying to give you an example of what's happening here. But you can read in through here. This goes into the next one. But every one of these codes and every one of these monitors are in here, and they explain it all, to you in this ad nauseum. So it is available, for your, bathroom reading to be able to sit and understand and know all this stuff. But you really only need it, when you're, one of the things it said was when you're faced with a code, especially if it's giving you problems, hey, let's go find out what in the world's what's causing it. What is it that they're looking for? And I will tell you that, especially with these two codes, I don't fully understand what they're looking for. It's exceedingly difficult. I got some other information from Ford, say, okay, what are we looking for? And at the end of the day, you're looking for no more than 10 parts per million of NOx going out the tailpipe. Well, this vehicle I'm fighting has less than that. I've never had it have more than that. I don't know what I'm, chasing. And unfortunately, there's really not a lot of people at Ford who know the answer to a lot of this stuff either. Some of it's very difficult and very government driven. And if you're having a problem with one, it's very difficult. I don't mean to discourage anybody when they're thinking about getting into this field, but just know that, all this stuff is government driven. And its reasoning is for emission control. So we're trying to make sure that we're not polluting these vehicles running around. Okay. So does that make sense, everybody? Did that just throw a big monkey wrench in there, or does this make sense to you? Or do you even care?
It makes sense.
Okay. You probably won't run into this kind of stuff in an aircraft that I know of. Will you? What do you guys do there? They just want to know how it runs, right?
Yeah.
Yeah. How is that going up there? Are you done yet, or you got another week or two?
I have another week.
Yeah. Are you going to pass the class up there?
Yeah.
You guys are out of, you're not doing in class anymore, are you?
We are doing labs over there.
Are you? Are they
Yeah.
pretty good?
Yeah. They're really hands-on.
Yeah. I'm sorry that we don't have any hands-on. Blame your brother. He's telling him, hey, you need to start running the show over there and let us in. So anyway, so that's all I have on OBD2 systems. Does that make sense? They're monitoring systems to make sure that the system's running good at the end of the day. And we can use those to help us make sure that we've repaired the vehicle. Because everything that we've talked about, whether the fuel injectors, the glow plugs, the EGR, the all the exhaust after treatments, all of that stuff is all monitored by the OBD2 system. And there you go. And that's all I have for you on diesel drivability. That makes sense, everybody? Everybody all dieseled up now? And keep my phone number in the future. You're in the business and you got questions, feel free to ask the questions, because I'm always willing to help a new tech out. Okay.
Cool.
All right. Crystal, it's been fun.
Thank you.
All right. And again, you don't have to be here on Friday or Thursday. So enjoy all the rest of your finals.
Thank you. I'll be around for.
Okay.
All
All right. All right. Gavin,
Yes, sir.
make sure you are there on Thursday with your thinking cap on. Like I said, you have until next Monday to get all the rest of those things. Anything you're going to turned in.
All right.
Make sure you get it turned in, and then but be there on Thursday to make sure that you take the final.
Definitely.
And I'll give you a couple hours and make sure you're good. Okay.
All right. Thank you very much, sir.
All right, sir. We'll see you guys.
All right. See you then.
All right. Bye.